For anyone, deep in the trenches, optimizing these massive large language models, the hunt for efficiency, for better performance, it's just constant, right? It feels like the central challenge. We've all been there, relying heavily on Adam W. I mean, it's been the absolute workhorse, hasn't it? Carried so much of the LM progress. It really became the standard. And for very good reasons, it's robust, it adapts, it handles a sheer scale. But what if there's a fundamentally different way? An approach that doesn't just speed things up, but maybe improves the training itself. Maybe gets us better models with, well, less effort. And that's exactly what we're digging into today. Our mission is to really unpack this technical report. Muon is scalable for LLM training. It's from researchers at Moonshot AI and UCLA. And look, this isn't just some abstract idea. It's a detailed report showing how the Muon optimizer, which, looked promising on smaller stuff, has now been scaled up. We're talking billions of parameters, trillions of tokens. We're going to look at the techniques, the clever tricks that made this possible, get into the mechanics, the distributed computing side of things. And we'll also meet Moonlight, a new mixture of expert model that really shows what Muon can do in practice.
Yeah. And what's really great here, I think, is the source itself. Like you said, it's not just throwing ideas around. It's a solid technical report. It lays out the analysis, the methods they developed, and crucially, it's packed with experimental results, rigorous validation. And when you're talking L&M training, I mean, the stakes are incredibly high, right? Every bit of efficiency matters. Think compute hours, cost. So having insights that are really backed by solid empirical data, by experiments you could, in theory, reproduce, that's absolutely essential. It connects the theory directly to practice.
Exactly. And that's why this deep dive is really for you, our listener. We know you understand this stuff deeply. We're not just giving you the headlines. We want to cut through the sometimes dense research language and get to those aha moments, the things that actually matter if you're working at the forefront. So yeah, get ready to really understand the mechanics behind this potential shift in AI training. Maybe even question some assumptions about optimization. Okay, so let's paint the picture first. When we talk LLM optimization, you basically can't not talk about Adam, especially Adam W. They've just dominated. They're the go-to for pretty much every major LLM out there, the standard. But why? Why did they become so entrenched? What made them the default for so long?
Well, yeah, they became dominant for good reason. Optimizers are just so critical. It ties back to the scaling laws. Bigger models, more data, more compute generally means better performance. But that also means the training itself becomes incredibly computationally intensive, astronomical, really. So a good optimizer means faster training, lower costs. It makes things feasible. Adam W. is brilliant at this. It has adaptive learning rates for every single parameter. It handles sparse gradients well using those running averages. That adaptivity was key for deep learning's complex loss landscapes. But fundamentally, it's an element-wise approach. And that has implications for how the model weights, specifically those weight matrices, behave dynamically during training, like how their singular values evolve.
Right. And that brings us neatly to Muon. It seems to come from a completely different philosophical starting point. It doesn't work element-wise in the same way. Can you walk us through that core concept? What makes Muon tick at its most basic level?
Exactly. It's a fundamental shift. At its core, Muon updates neural network weights, the ones representable as matrices, using matrix orthogonalization. That's the key difference from Adam, which scales individual parameters based on their own gradient history. If you look at the update rule, equation 1 in the report, it's essentially DOBT1 and ATO. So DODIDO is the weight matrix, DIODA is the learning rate. But the crucial part is how OT dollar, the orthogonalized output, is generated. It comes from applying a special operation to a momentum term, MTT. And the real engine here is that Newton-Schultz operation. It's an iterative method to approximate MT, MDT, 12 MT2. Okay, so what does that mean intuitively? Think of the SVD, the singular value decomposition of a tau dollar, which is $1 sigma VT. The sigma part holds the scaling factors, the singular values. U and V are rotations. What Newton-Schultz does, essentially, is it calculates UV thalers. It strips away the scaling part and just keeps the orthogonal components. It effectively orthogonalizes the momentum matrix MT talar. So the resulting update matrix E Deller is very close to being an orthogonal matrix itself. The paper also mentions they use a Nesterov-style momentum in practice. So Newton-Schultz is actually applying to a combination of the momentum and the current gradient, double MT plus nabla LTWT1, giving it that look-ahead property too. But why orthogonalization? Why is that the goal? This goes back to the original Muon paper's intuition. By making the update matrices isomorphic, meaning they preserve the geometric structure, the shape of the space they act on, Muon tries to prevent the weights from learning just along a few dominant directions. Think about Adam again. It scales each parameter individually. Some might get huge effective learning rates, others tiny ones. This can amplify certain pathways and diminish others. Muon, by enforcing orthogonality, aims for a more, let's say, balanced update across the entire matrix's potential directions, its singular spectrum. It helps keep the weight matrices well-conditioned, avoiding exploding or collapsing singular values, which can cause instability or kill learning. It's really about encouraging updates that are more like rotations than just scaling.
Okay, that is a really different way of thinking about it compared to Adam. So if I'm following, it's fundamentally about stopping those singular values from going wild, either exploding or vanishing. It's about keeping the weight matrices healthier, numerically speaking, by favoring updates that don't just scale things up or down drastically along certain axes. It sounds like it tackles some known issues in deep nets head on.
Precisely. And digging a bit deeper into those Newton-Schultz iterations, equation 2 gives the formula. It's xk, xk1 plus b, xk1, xtk1 plus c, c1, xck1 plus the xk1, 2, xk1. It starts with xk based on the momentum matrix, normalized. Then it iterates n times using these coefficients abc. The paper uses specific values, a 3.4445, b 4.7750, c 2.0315. These aren't random. They were carefully tuned in the original work for fast and stable convergence, especially important if the initial matrix has very small singular values. This iterative process is what allows Muon to accurately compute that orthogonal part, the Yulun. Now, stepping back, how does this fit theoretically? There's interesting work by Bernstein and others viewing optimization as steepest descent, but under certain norm constraints. From this angle, the difference between Adam and Muon becomes really clear. It's about what norm they constrain. Adam uses a kind of max of max norm, tied to the maximum gradient seen for each parameter, element-wise scaling again. And here's the aha moment, I think. Muon, when it works properly, effectively imposes a spectral norm constraint on its updates.
For neural network weights, which are basically linear operators acting on vectors, the spectral norm is arguably a more natural or reasonable constraint. Why? Because the spectral norm directly measures the maximum scaling factor the matrix applies to any input vector. It relates directly to the matrix's function as an operator. By constraining this maximum singular value, Muon controls the maximum amplification. It suggests Muon sort of intrinsically respects the geometry of weights as operators, leading to potentially more stable updates than Adam's Ellen-wise approach. It encourages well-conditioned transformations.
That theoretical connection is really compelling. It suggests Muon isn't just a clever heuristic, but maybe more aligned with the math of neural nets. But okay, the huge challenge, as the paper points out, was taking this elegant idea from smaller models and making it work for, giant LLMs. What were the actual roadblocks? What happened when they first tried to just scale up vanilla Muon? You mentioned exploding RMS. I can picture the nans flashing. Nightmare fuel for any ML engineer.
Oh, absolutely. Scaling it up reveals some serious practical hurdles. The paper lays out three main ones. First, just the raw computation of doing matrix orthogonalization for billions of parameters trained on trillions of tokens. That's intense. Second, how do you do this efficiently in a distributed setting? You have to distribute LLM training. That was a big engineering problem. And third, making sure it works well across the whole life cycle, pre-training, supervised fine-tuning, SFT. It needed to generalize. And yeah, their initial attempts without modifications, the performance gains started to fade as things got bigger. And the big warning sign was exactly what you mentioned. The root mean square, RMS values of both the weights themselves and the outputs of the layers just kept growing uncontrollably. Anyone who trains large models knows that's bad news. Values started hitting the limits of BF16 precision, the standard format used for efficiency. When that happens, you risk numerical instability, gradients getting clipped weirdly, or just plain nans that crash the whole training run. It showed an inherent instability at LLM scale.
Right, so faced with that exploding RMS problem, that instability, what was the first big fix, the first crucial technique they applied to tame Muon and make it suitable for these huge models? Was it something totally unexpected?
Well, maybe not unexpected in hindsight, but crucial. They basically added back a standard technique, Adam W-style weight decay. Interestingly, the original Muon paper, focusing on smaller scale, had actually omitted weight decay. Turns out that was a key piece missing for stability at LLM scales. The update rule then becomes, as shown in equation 3, torod plus lambda Gorda 1. That lambda 1 term is the weight decay. It just gently nudges weights towards zero, acting as a regularizer. Classic technique, but its absence was a major factor in Muon's initial scaling problems. And the evidence for this is really clear in figure 2 of the paper. They did this experiment training an 800 EMMA parameter model for much longer than usual, like 5x the optimal tokens, to see the long-term behavior. Vanilla Muon without weight decay starts off faster, which shows its inherent efficiency, right? But then its validation loss starts to suffer. Performance degrades, probably due to those weights growing too large, causing instability. But Muon with weight decay, completely different story. It stays stable throughout, and importantly, it ends up outperforming both vanilla Muon and Adam W in this overtraining scenario. It gets a lower final validation loss. So weight decay wasn't just a patch. It transformed Muon into something robust and actually superior for long, large-scale training. It kept the speed, but fixed the explosion problem.
Okay, that makes sense. Stabilizing things with a known technique. But then there was this other subtle issue you mentioned. Adam W's updates have a theoretical RMS around 1, but Muon's varied based on the shape of the matrix. That sounds like it could cause real problems, like different parts of the network learning at totally different effective rates. How did they fix that inconsistency?
Yeah, this was a really sharp observation, and they formalized it in Lemma 1. Basically, for a matrix with shape AB, Muon's theoretical update RMS scales like squirty makes. So a tall, skinny matrix or a short, wide one would naturally have a different update scale compared to a more squarish one, just because its dimensions. And the practical consequences for LLMs are significant. Think about a huge MLP matrix in a transformer block is large. Lemma 1 implies Muon's updates for that matrix would naturally be too small. It wouldn't learn effectively in those big parameter-heavy layers, kind of starving them. Now flip it. Think about individual attention heads in groups query attention, maybe treated as smaller matrices. Here, max could be relatively small. In that case, Muon's updates would naturally be too large. That's asking for trouble instability, divergence in those crucial but smaller components. So the fix is actually quite elegant. They propose scaling the Muon update for each matrix by Lismo max. This factor directly cancels out the squarity from the lemma, making the update RMS consistent across all matrix shapes. Equation 4 shows this. But they took it a step further. They noticed empirically that Adam W's update RMS tends to hover between 0.2 and 0.4. So to make life easier for practitioners and allow reusing hyperparameters tuned for Adam W, they added another constant scaling factor of 0.2 to Muon's update. This is huge practically. It means you can often take your carefully tuned Adam W learning rate and weight decay and just plug them in for Muon. Reduces a ton of tuning effort. So the final refined update rule looks like WT1 plus lambda WT1. This handles both weight decay and the per matrix scaling. They also tested different ways to control this RMS in Table 1. There was a baseline global scaling, directly normalizing updates to 0.2, update norm, and this per matrix learning rate scaling adjusted LR, equation 7. Both update norm and adjusted LR were much better than the simple baseline. They ended up choosing adjusted LR for most experiments because it had similar benefits to update norm, but was slightly cheaper computationally. It really underscores how carefully managing that update RMS is key for stable, high-performance training with Muon at scale.
And just quickly on other hyperparameters, they found that N5 Newton-Schultz iterations was enough. Going up to N10 didn't really improve performance, so 5 was the sweet spot for efficiency. And for momentum, they stuck with 1 mu.955 from the original paper, as tuning it further didn't seem to yield big gains. Suggest some robustness there.
Okay, now this is where, for me, it gets really critical for making this work in the real world. Distributed training. You just can't train these models on one machine. We know 0-1 is great for Adam W because updates are element-wise, right? Each GPU handles its own slice. But Muon needs the whole gradient matrix for that orthogonalization step. That sounds like it breaks the 0-1 paradigm. How on earth did they implement Muon efficiently across multiple GPUs and nodes? This feels like a major piece of engineering.
You've nailed the core challenge. Standard 0-1 partitions the optimizer state's weights, momentum across the GPUs in a data parallel group. Works perfectly for Adam W because it just needs the local gradient slice to compute its local update. But Muon's Newton-Schultz step needs the full gradient matrix. You can't just orthogonalize a slice. It wouldn't make sense mathematically for the global update. So yeah, vanilla 0-1 just wasn't directly compatible. They had to fundamentally rethink how the optimizer interacts with the distributed setup. So they came up with distributed Muon, outlined in algorithm 1. Builds on 0-1 but adds 2 crucial new steps. First, after the gradients are computed and reduced scattered across the data parallel group, standard stuff, there's a new step, DP gather. For each layer whose weights are partitioned across the data parallel group, this step gathers all the corresponding gradient partitions onto a single device, or across the tensor parallel group if used, reassembling the full gradient matrix. This is essential. Then comes the second new step, calculate full update.
With the full gradient matrix now available, the Newton-Schultz iterations are performed on that complete matrix. This calculates the full orthogonalized Muon update, others dollars. Now cleverly, after computing this full update, the algorithm only keeps the portion of the update relevant to the parameters stored locally on that GPU. The rest is discarded. Then it applies the update rule we discussed. After the update, it does an all-gather of the updated parameters similar to standard 0-1, so all GPUs have the latest weights for the next forward pass. What's really impressive is how they integrated this matrix-level operation into the existing parallel strategies: tensor parallel, pipeline parallel, expert parallel, data parallel. It's smart engineering to make a global operation feel somewhat localized to the UP group. Okay, let's talk trade-offs versus distributed Atom W, because efficiency is everything. Memory-wise, there's actually a surprising win for Muon. Atom W needs 2 buffers for its momentum states, first and second moments. Muon only needs 1 momentum buffer. So, distributed Muon's optimizer states take up about half the extra memory compared to distributed Atom W. That's a pretty significant saving, especially when you're memory constrained. Communication overhead. Yes, there's that extra DP gather, but it's only for the partition parameters, and its cost is actually less than a full gradient reduced scatter or parameter all gather. Plus, a key optimization. They run the Newton-Schultz computation itself in BS16 precision. This cuts the communication needed for that specific step by half compared to FP32. The paper analyzes the total overhead and concludes it's only between 1x and 1.25x that of Atom W. Empirically, they found it was closer to the lower end, so the added communication is surprisingly small in practice. And finally, latency, the impact on actual training time. Does the extra gather and computation slow things down? Well, technically, yes, it adds a bit. But the paper reports the impact is negligible, typically adding only 1% to 3% to the forward-backward pass time. Remember, they only need about 5 Newton-Schultz steps, and they use clever engineering tricks like overlapping the DP gather with other work and overlapping the optimizer's communication with the parameter all gather. So in their large cluster, they found distributed Muon had basically no noticeable latency overhead compared to Atom W. That's huge. It means it's practical, deployable right now without slowing down your training.
Wow. Okay, so let me get this straight. We get potentially much better optimization dynamics, and it uses less memory, and it doesn't really slow down the training throughput. That's genuinely incredible. It means these benefits aren't just theoretical, they're achievable in practice right now in large-scale setups. That feels like a really big deal for the field, right? Theory and engineering are one thing, but like we always say, the proof is in the pudding. Does Muon actually deliver better results on real models and scaling experiments? How does it stack up against Atom W when you push it on massive models and look at scaling laws? This is where we see if it really lives up to the hype.
Exactly. And this section of the paper is all about that rigorous validation. They started with scaling laws. To make it a fair fight, they first established a very strong Atom W baseline using standard llama architecture dense models. And they didn't just pick some default hyperparameters, they did a massive grid search to find the optimal Atom W settings for different compute budgets. You can see the details in Appendix B, Cable 9, finding the best model size, tokens, learning rate, batch size for each compute level. You need a strong baseline to claim improvement. And remember that trick with scaling Muon's update RMS. It meant they could often just reuse the optimal hyperparameters found for Atom W directly with Muon. That's a massive practical plus. So the results, they are pretty striking. Figure 1A and Figure 3 show the fitted scaling law curves. The headline finding is this. Muon achieves basically the same performance as Atom W, but using only about 52% of the training FLOPs. Let that sink in. Roughly half the compute to reach the same loss level. That's nearly a 2x gain in computational efficiency. Think what that means. Half the energy, half the cost, half the time to train a model to the same quality level. For labs with limited resources, for companies needing faster iteration, for sustainability, this is potentially transformative. It really could shift the economics of LLM training.
Almost 2x compute efficiency. That's a huge claim, backed by scaling law analysis. But they didn't stop there, right? They actually trained a big new model using Muon. Tell us about Moonlight. What kind of model is it, and what does it demonstrate about Muon in a real-world training scenario?
Yeah, Moonlight is the concrete proof point. It's a mixture of expert model, or MOE. They based it on the DeepSeek V3 small architecture, which is already pretty efficient. Moonlight has about 2.2 billion active parameters out of maybe 15, 16 billion total parameters, including embeddings. So 3B, 16B class roughly. They made a few tweaks, dropped multi-token prediction, used a modified bias update, and importantly, they tuned the MOE gate scaling factor. This was apparently key to keep the router output stable, similar to dense models. Training was intense. 5.7 trillion tokens in total, split into 3 stages. Stage 1, ramp up learning rate, standard batch size. Stage 2, longer phase, cosine decay for learning rate, doubled batch size for throughput. Stage 3, a cool-down phase focusing on high-quality data math, code, reasoning with a final linear learning rate decay. This kind of multi-stage schedule is pretty common for squeezing out peak performance. And then evaluation. They threw a massive suite of benchmarks at it. English understanding, MLU, BBH, code, human eval, MBPP, math, GSM8K, math, Chinese understanding, C-eval, CMLU, towards
This broad testing gives a really robust picture of the model's capabilities across different domains and languages. Okay, let's get into the performance number, because this is where Muon really makes its case. First, look at Table 4. This compares models at an intermediate 1.2 trillion token checkpoint. You've got Moonlight, Muon trained, DeepSeek V3 small, Atom W, similar scale, and Moonlight A, an Atom W trained version of Moonlight. The key comparison is Moonlight versus Moonlight A. And Moonlight, trained with Muon, is already significantly ahead, especially on math and code. Like human eval. 37.2 for Moonlight versus 29.3 for the Atom W version, GSM8K, 45.0 versus 43.8. It shows Muon gets better results faster, even early in training. Now the final results after 5.7 trillion tokens. Tables 5 and 10 compare Moonlight to other strong 3B class models. These include Llama 3.23b, trained on 9T tokens, Gwyn 2.53b on a massive 18T tokens, and DeepSeek V2 Lite, trained on a similar 5.7T tokens. The results are really impressive. Moonlight outperforms similar architecture models trained on the same amount of data, like DeepSeek V2 Lite.
Even more striking, Moonlight holds its own and often beats dense models trained on way more data, like Llama 3.2 and Gwyn 2.5 on many benchmarks. Think MMLU, BBH, Human Eval, GSM8K, Math. Despite being an MOE model trained on fewer tokens overall, 5.7T versus 9T or 18T, Moonlight is showing superior or highly competitive results across the board. For instance, MMLU. Moonlight gets 63.8, beating Llama 3.2, 63.5, and Gwyn 2.5, 61.6. That's impressive, given the data difference. And the crucial takeaway visually show in figures 1b and 8, the performance versus FLOP's graphs for MLU and GSM8K. Moonlight consistently sits on the Pareto frontier. What that means is it achieves better performance for significantly fewer training FLPs compared to many other models out there. It's not just a small edge. It fundamentally demonstrates Muon's ability to push the efficiency boundary. Better models, less compute. That's the promise delivered.
That is really compelling evidence. A 2x efficiency boost models on the Pareto frontier. It makes Muon look like a very practical and powerful tool. Now, earlier you mentioned the intuition behind Muon was encouraging more diverse updates through orthogonalization. Did they actually measure that? Did the weight matrices look different when trained with Muon compared to Atom W?
They did, yes. And it's a really neat piece of empirical validation for the theory. They used a metric called SVD entropy, borrowed from earlier work by Alter et al., to quantify this diversity in the singular values of the weight matrices. Basically, you take the singular value sigma of a matrix, normalize their squares so they sum to 1, like a probability distribution, and then calculate the Shannon entropy of that distribution. A higher SVD entropy means the distribution is flatter. The matrix is using more of its singular values, more of its potential directions. Lower entropy means it's concentrating power in just a few dominant singular values. And the results, look at figure 4 and figures 9 and 10 in the appendix. Across different layers, attention, experts, routers, dense layers, and the different training checkpoints, Muon consistently leads to higher SVD entropy compared to Atom W. It provides solid empirical backing for the idea that Muon helps explore and maintain more diverse learning directions, preventing that collapse onto a few modes. They specifically call out the router weights in the MOE model showing a particularly large difference, much higher entropy with Muon.
This suggests MOE models might especially benefit from Muon's tendency to encourage diversity, particularly in the crucial routing mechanism. For something like 90% of the matrices they checked, SVD entropy was higher with Muon. It really seems to foster a richer internal representation.
Okay, so Muon looks great for pre-training more efficient, better models, more diverse weights. But what about supervised fine-tuning, SFT? That's super important for making models useful. Do the benefits carry over? Or is Muon mainly a pre-training powerhouse? This is a key practical question.
A very critical question, yes. And the paper digs into this with specific SFT ablation studies. The short answer is, the benefits can persist, but there's a big catch: optimizer consistency matters. Table 6 shows this clearly. If you take a model that was pre-trained with Muon and then also fine-tune it with Muon, it performs best. For example, their Muon pre-trained Moonlight 1.2T when Muon fine-tuned got an MLU of 55.7. But if they took that same Muon pre-trained model and fine-tuned it with Atom W, the score dropped slightly to 55.3. The Atom W pre-trained and Atom W fine-tuned baseline was lower still at 52.0. So sticking with Muon all the way through seems to give the best result. There's a compounding benefit. But here's the catch. If you switch optimizers between pre-training and SFT, the advantage mostly disappears. So Atom W pre-trained, then Muon fine-tuned, Muon pre-trained, then Atom W fine-tuned, neither performed optimally. Table 7 shows this again when they tried fine-tuning public Atom W pre-trained models like Gwyn 2.5/7 with Muon. The performance was okay, about the same as fine-tuning with Atom W, but there was no significant improvement from using Muon just for SFT.
This suggests that the real gains come from applying Muon during pre-training itself. It seems Muon shapes the model's internal structure in a way that benefits most from continued orthogonalization-based updates. You can't just swap it in at the end and expect magic. It points to a deeper interaction between the optimizer and the learned representations.
Okay, so after this really thorough investigation, proving mute scalability and benefits, what's next? Where do the researchers see this going? Are there still open questions or ways to push this orthogonalization idea further?
Yeah, they definitely point towards some interesting future directions. Three main ones stand out. First, a full Muon integration. Right now, their implementation is still technically a hybrid. Some parameters, like in RMS norm layers, the final language model head embeddings, are still handled by Atom. So an obvious next step is to try and bring everything under the Muon umbrella. Could that unlock even more efficiency or performance? Maybe simplify things. It's an open question. Second, a more theoretical direction, extending Muon beyond the spectral norm. We talked about how Muon implicitly uses a spectral norm constraint. But there are other ways to measure matrix size or norm, like the broader family of Schatten norms. Frobenius is Schatten 2, nuclear norm is Schatten 1. Could generalizing Muon to work with other Schatten norms lead to new optimization capabilities, maybe different inductive biases? That's a fascinating research path, potentially allowing more fine-grained control over the optimization geometry. And third, and this one feels really important practically, tackling that pre-training fine-tuning mismatch. The fact that you lose the benefit when switching optimizers is a barrier, right? It means you can't easily take all those existing models pre-trained with Atom W and just get a boost by fine-tuning with Muon. So understanding why this mismatch happens and finding ways to bridge that gap maybe through specific initialization or adaptation strategies is critical. Solving that would make Muon vastly more applicable to the existing ecosystem.
Right. So let's wrap this up. After diving deep into this report, what's the big picture takeaway for our listeners for the ML field? What does Muon really represent?
I think there are a few key conclusions to hammer home. First, Muon is definitively scalable. The paper puts any doubts about its practicality for large LLMs to rest. Second, it's a viable and arguably superior alternative to Atom W as a standard optimizer, especially for training new models from scratch. Third, the benefits are substantial and concrete. Nearly 2x compute efficiency to reach similar performance, and models like Moonlight pushing the state-of-the-art on the performance versus compute frontier. That's huge. And finally, the open sourcing is crucial. Releasing the distributed implementation, the Moonlight model, the checkpoints that gives the whole community tools to build on this work immediately. It's not just a paper, it's enabling the next wave. #TagOutTrack.
And that really sums it up. This paper, Muon is scalable for LLM training. It provides really strong evidence that we might be entering a new phase of LLM optimization. Moving beyond purely element-wise methods toward these orthogonalization-based approaches seems to offer a powerful way to boost both efficiency and performance. It's where elegant math meets the brutal demands of scale.
Exactly. And it makes you wonder, right? If an optimizer like Muon, by encouraging this diversity in the weights, this higher SVD entropy, already yields these benefits, what happens if we get even better at this? If optimizers become even more precisely tailored to the specific geometric nature of neural network operations, what new capabilities might emerge? What kind of models could we build? It's a really exciting thought.
Absolutely. A lot to think about there. We definitely encourage you, our listeners, to check out the paper, maybe play with the open-sourced Moonlight model if you can. It might just make you rethink the role of the optimizer in your own work. The ground is definitely shifting. Thanks for joining us on this deep dive.